For as long as humans have looked up at the night sky, we've wondered how big the universe really is. Ancient philosophers once imagined it as a small dome above the Earth, painted with stars like tiny lamps. Centuries later, astronomers declared our galaxy was the whole of existence, a lone island of light adrift in darkness. Each generation thought they had finally solved the puzzle, and each time they were spectacularly wrong. Even now, with powerful telescopes peering deeper into the cosmos than ever before, we are still struggling with the same question. The truth is stranger, more unsettling, and far more mysterious than we ever imagined. Today we say the universe is 13.8 billion years old, and that its observable edge lies 46 billion light-years away. But those numbers are fragile. They wobble with every new discovery, shift with every recalculation, and sometimes shatter completely when evidence defies the rules we thought were unbreakable. We've seen galaxies that form too quickly, black holes too large to exist, and cosmic structures so immense they shouldn't even be possible within the laws of physics. Each discovery pulls the rug out from under us, leaving scientists scrambling to explain what went wrong, and whether our very understanding of reality is flawed. What makes this story so powerful isn't just the size of the universe, but the way it humbles us. With every step forward, the cosmos grows larger, stranger, and less knowable. We're forced to confront the possibility that what we can observe is only a fraction of what actually exists, a bubble of light surrounded by an infinite unknown. And the most shocking part? No matter how advanced our tools become, there will always be a horizon we cannot see beyond, an edge that traps us in our own cosmic cage. The universe is bigger, older, and more alien than our minds are ready to accept, and the deeper we look, the less we seem to understand. When we talk about humanity's first attempts to measure the universe, it almost feels like reading a story written in the language of hubris. People looked up at the stars full of confidence that they already understood their place among them, yet every idea they crafted was tiny compared to the immensity of reality. To the ancient Greeks, the universe wasn't infinite at all. It was a neat, finite dome, a celestial sphere wrapped neatly around the Earth like a crystal globe. Stars were imagined as fixed points of light embedded in that dome, rotating around us like ornaments on the ceiling of a theatre. It was a model that placed humanity not just at the centre of existence, but at the very heart of meaning. Why look beyond when everything revolved around us? Aristotle refined the idea, describing a cosmos of concentric spheres. To him, the Earth sat unmoving at the centre, while the moon, sun, planets and stars were attached to invisible crystalline shells, each spinning perfectly. This system didn't just define space, it defined certainty. The universe was small, finite and orderly, a few thousand miles across at best. There was no concept of galaxies, no awareness of distances that spanned millions of light years. For Aristotle and those who followed, the stars were close enough to almost touch, shining lanterns set in motion by divine design. And because this model explained the motions of the heavens, people accepted it as truth for nearly 2,000 years. It was a breathtaking error, one that would survive far longer than it should have, but mistakes piled upon mistakes. Claudius Ptolemy took Aristotle's framework and added even more complexity, crafting the geocentric system that would dominate astronomy through the Middle Ages. He built a universe where everything circled Earth in perfect geometry, yet when planets didn't follow the rules, he bent his model with loops and cycles, epicycles upon epicycles, mathematical band-aids to hide the fact that the universe refused to obey the limits he imposed. To those who believed him, the universe was still small, still manageable, still comforting. To those who doubted, the contradictions only grew harder to ignore. The most staggering part of this early story is how convinced people were that they had it figured out. To them, the universe wasn't terrifying in its size, it was simple, elegant, and compact. Earth was the stage, and everything else was just background decoration. But the cracks began to show. New observations revealed stars that didn't fit the neat pattern of fixed spheres. The moon's craters hinted that celestial bodies weren't perfect and divine, but flawed, material worlds. Slowly, the dome of certainty began to crumble. The Renaissance brought a radical shift. Nicholas Copernicus dared to place the sun at the centre instead of the Earth. To us that sounds like a natural correction, but at the time it was almost heretical. his model suddenly expanded the scale of things. Earth was just one of many planets orbiting the Sun, not the cosmic anchor. But even then, the universe remained small in his mind, still a tight arrangement of planets, still a limited sphere of stars just with a different focal point. He cracked the door open, but he hadn't yet revealed the vastness that lay outside. Then came Galileo Galilei, and with him, the telescope. His discoveries were like dynamite to the old world view. Through his lens, Jupiter had moons circling it, proving not everything orbited Earth. Venus showed phases like the moon, confirming it circled the Sun. And the Milky Way, once thought to be a faint smear of light in the sky, was suddenly revealed to be a swarm of countless stars. The universe was expanding before humanity's very eyes, and it terrified those who clung to the old ways. Galileo was condemned not just for his science, but for daring to suggest the universe was more than the neat, closed box people had always believed in. Even so, mistakes persisted. For centuries, scientists thought the stars of the Milky Way marked the edge of the cosmos. Beyond them, they imagined only void. The universe was still a finite sphere, just larger than before. Astronomers argued over its size, tossing around figures like a few thousand light-years, while reality stretched unimaginably further. Every attempt to measure the universe came up short, not because of a lack of effort, but because human imagination simply could not grasp the true scale of what was out there. These first mistakes are more than historical curiosities. They are cautionary tales. They remind us how easy it is to believe the story that feels neat, that feels manageable, even if it's completely wrong. The ancients weren't foolish. They were limited by the tools they had and the perspectives they inherited, and perhaps we are no different. Just as Aristotle thought he had reached the edges of the cosmos, perhaps we too live under illusions that future generations will look back on and laugh at. When scientists today debate whether the universe is infinite or whether dark matter and dark energy even exist, it's worth remembering how often certainty has been shattered in the past. The first mistakes also set the stage for everything that followed. Once the geocentric model fell, once humanity accepted that Earth was not the centre, the universe could grow, and grow it did, with each discovery multiplying its size, complexity and strangeness. But at every stage, people carried forward the same arrogance, the belief that now, finally, we understood it. It's almost a pattern written into human history, a cycle of revelation followed by overconfidence, followed by another shattering of assumptions. So when we look back at Aristotle's dome or Ptolemy's loops, it's tempting to laugh at how small their universe was. But the real lesson isn't about their ignorance, it's about ours. Just as they could not imagine galaxies beyond their stars, we may be blind to structures, forces, and dimensions beyond our reach. The first mistakes were not just wrong answers. They were proof that the human mind struggles with scales so large, so alien, that even now we may still be living inside a cage of misunderstanding. The universe has always been bigger than the box we try to put it in, and if history has taught us anything, it's that our current box is just as fragile as theirs once was. At the turn of the 20th century, astronomy was still wrestling with the shadow of its own limitations. Telescopes had grown larger, lenses sharper, and photographic plates allowed the heavens to be captured in exquisite detail. But distance remained an unsolved riddle. Astronomers could see countless stars scattered across the sky, some faint, some blindingly bright, but they could not tell if a faint star was small and nearby or gigantic and unimaginably far away. The cosmos was a flat picture with no depth. They had built instruments capable of peering across oceans of light, but without a ruler, the universe remained incomprehensible. And into this problem stepped an unlikely figure, a quiet woman working in near anonymity in a dusty office at the Harvard College Observatory. Her name was Henrietta Swan Leavitt, and her work would transform the universe from a flat painting into a three-dimensional ocean. Leavitt was not recognized as a professional astronomer in her time, at least not in the way we think of one today. She was part of the Harvard Computers, a group of women employed by Edward Pickering to examine photographic plates of stars. Their job was meticulous, repetitive, and undervalued, cataloguing brightness, recording positions, classifying spectral types. It was work dismissed by many of their male counterparts as clerical, not creative, yet it required extraordinary attention to detail. Leavitt approached the task with precision and patience. examining variable stars, those whose brightness shifted over time, across the small Magellanic Cloud. A faint smudge of a light visible in the southern sky. It was tedious work, but in the faint fluctuations of those stars she began to notice a pattern. The stars she studied pulsed with regular rhythms, brightening and dimming in cycles that repeated with clock-like accuracy. These were Cepheid variable stars, though their importance was not yet understood. What Leavitt discovered was revolutionary. The longer the period of a star's cycle, the brighter its true luminosity. In other words, if you measured how quickly a Cepheid pulsed, you could calculate how luminous it really was. And once you knew that, you could compare its true brightness with how faint it appeared from Earth and calculate its distance. Suddenly, astronomers had a cosmic yardstick. What had once been guesswork could now be measured with astonishing precision. At first, Leavitt's discovery was buried in the back pages of obscure scientific bulletins, another data point in an ocean of cataloguing. But those who recognized its significance knew immediately that it was groundbreaking. This wasn't just a tool for measuring nearby stars, it was a key that could unlock the true scale of the universe. No longer would astronomers be trapped inside the illusion that the Milky Way defined all of existence. Cepheid variables offered a way to look beyond, to measure the distances to entire galaxies. Leavitt had provided the missing ruler, and with it, the flat sky would suddenly stretch into unfathomable depth. The irony was cruel. Leavitt herself received little recognition in her lifetime. She was not allowed to operate telescopes, not invited to the great observatories of her day, not given the full title of astronomer. Yet her quiet work in the stacks of glass plates became the foundation for discoveries that would rewrite everything. Her law of Cepheid variables would later be used by Edwin Hubble to prove the existence of galaxies far beyond our own. Without her, the universe might still appear to us as a small, lonely sphere. With her, the cosmos exploded outward. The transformation her discovery initiated cannot be overstated. For centuries, people had believed the Milky Way was the universe itself, a lone island of stars floating in infinite darkness. Philosophers and astronomers debated its boundaries, its shape, and its size, but few imagined that there could be more beyond it. Leavitt's work didn't just extend the scale, it shattered it. If Cepheids could be found in the faint smudges of light beyond the Milky Way, then those smudges were not clouds of gas or star clusters, but entire galaxies, each with billions of suns. And if that was true, then the universe was not just bigger than we thought, it was incomprehensibly larger, a cosmos filled with countless islands of stars. There's a kind of poetic justice in the fact that such a seismic shift came from someone overlooked, someone whose name was nearly lost to history. Henrietta Swan Leavitt did not travel the world to present her findings at international conferences. She did not stand at the eyepiece of the world's greatest telescopes. She worked quietly in the background, piecing together patterns that others missed, and in doing so she gave humanity a way to see the true universe for the first time. Her breakthrough was less dramatic than Galileo's telescope or Copernicus's heliocentric revolution, but in many ways it was more profound. She gave us scale, and scale is everything. With Cepheid variables as a cosmic ruler, astronomers could measure distances not in thousands of light years, but in millions. The Milky Way was no longer the boundary of reality. It was just one speck in a vast ocean. And if that was true, then every faint smudge, every spiral faintly captured on glass plates, might be another Milky Way, another island of billions of stars. The universe had grown overnight, and there was no turning back. The tragedy, of course, is that Leavitt did not live to see the full impact of her work. She died in 1921, just as Edwin Hubble was beginning to apply her Cepheid law to galaxies beyond the Milky Way. She never knew that her discovery would be the cornerstone of one of the most important astronomical revolutions in history. And yet, in a way, that makes her contribution even more poignant. She did not seek fame, she did not demand recognition, but she altered the trajectory of science forever. Her breakthrough was not just about stars, it was about perspective. By showing us how to measure distance, she forced us to accept that we had been wrong again, that our galaxy was not the universe, but only one part of something unimaginably vast. Every time humanity thought it had reached the edge of the cosmos, the edge slipped further away, and with Leavitt's discovery, that edge vanished into infinity. The sky was no longer a dome, no longer a single island, but a limitless sea dotted with galaxies, each one further than the last, each one measurable by the pulse of a distant star. Henrietta Swan. Leavitt's quiet work gave us the ruler to measure the cosmos. It transformed the way we see ourselves, and it prepared the stage for discoveries that would soon explode our understanding of the universe beyond recognition. Her breakthrough was the whisper that preceded the thunder, the clue that turned into a revelation, the first true step into the infinite. And once that door was opened, nothing would ever look the same again. When Henrietta Swan Leavitt uncovered the secret of Cepheid variables, she handed astronomy a tool that would soon change everything. But it would take another figure, armed with that discovery and with the sharpest telescopes of his time, to use it to shatter humanity's last illusions about the size of the cosmos. His name was Edwin Hubble, and in the early 1920s his work would rip open the walls of the known universe. Up until then, even with Leavitt's breakthrough, most astronomers still clung to the belief that the Milky Way galaxy was the entire universe. There were fierce debates about faint spiral-shaped smudges visible in the night sky. Some argued they were spiral nebulae, small clusters of gas and dust orbiting within our galaxy. Others dared to suggest they might be island universes, entire galaxies of their own, far beyond the boundaries of the Milky Way. The arguments were heated, but without a way to measure their distances, the question remained unsettled. That changed when Hubble turned his telescope toward one of the brightest spirals in the sky, the Andromeda Nebula. The Andromeda Nebula had been observed for centuries, a ghostly oval visible to the naked eye on clear nights. Some saw it as a patch of celestial fog, others as a swarm of stars too faint to distinguish. To Hubble, armed with Leavitt's cosmic yardstick, it was an opportunity to answer a question as old as stargazing itself. Was the Milky Way the universe, or was it just one galaxy among many? Night after night he photographed Andromeda with the 100-inch Hooker telescope at Mount Wilson Observatory, the most powerful in the world at that time, and in those photographs he found something extraordinary. Among the countless faint points of light in Andromeda, he identified Cepheid variable stars. Using Leavitt's method, he measured their pulsations, calculated their true luminosities, and compared them with their apparent brightness. The result was staggering. Andromeda wasn't nearby. It wasn't part of the Milky Way at all. It was 2.5 million light-years away, so far that it had to be its own galaxy, with billions of stars. In a single calculation, Hubble proved the universe was not confined to the Milky Way. Our galaxy was just one island in an endless cosmic ocean. The implications were breathtaking. If Andromeda was a galaxy, then so were the other spiral nebulae scattered across the sky. The faint smudges catalogued for centuries were not small clouds, but entire universes in their own right. Overnight, the cosmos expanded from one galaxy to potentially billions. Humanity's place shrank from the centre of everything to a small corner of one spiral, among countless others. It's hard to overstate how shocking this was at the time. Imagine thinking your hometown was the whole world, only to learn there are entire continents, oceans and civilizations stretching endlessly beyond. The universe had grown not by a factor of 10, not by a factor of 100, but by a factor of millions. What had once seemed vast, the Milky Way, with its 100 billion stars, was suddenly revealed as ordinary, just one among countless galaxies filling the night sky. The sheer enormity of it was almost unbearable, but Hubble didn't stop there. He began measuring more galaxies, applying the Cepheid yardstick wherever he could, and soon his observations revealed something even more startling. Galaxies weren't just scattered randomly, they were moving, and not just moving in any direction, but moving away from us. The farther away a galaxy was, the faster it appeared to be receding. This relationship, which came to be known as Hubble's law, suggested something revolutionary. The universe itself was expanding. No longer was the cosmos a static backdrop. It was dynamic, stretching, growing, and carrying galaxies with it like raisins in a rising loaf of bread. This was a direct challenge to centuries of belief that the universe was eternal and unchanging. If galaxies were rushing away, then at some point in the past they must have been closer together. Trace the expansion backward far enough, and it implied everything we see today began from a single dense point. Hubble hadn't just proved the universe was vast, He had set the stage for the Big Bang theory itself. The universe wasn't infinite and timeless. It had a beginning, and if it had a beginning, it might also have an end. For the public, the revelations were mind-blowing. Newspaper headlines declared that humanity was no longer at the center of creation, but adrift in a sea of galaxies. For scientists, the implications were even deeper. Every assumption had to be revisited. If the Milky Way was just one among billions, then our Sun was merely one star among trillions, and Earth one planet in an ocean of worlds. The idea of life elsewhere suddenly seemed less like speculation and more like a statistical inevitability. Hubble himself, however, was a cautious figure. He was reluctant to draw philosophical conclusions, preferring to let the data speak. Yet his work had philosophical weight whether he admitted it or not. By proving the existence of other galaxies and the expansion of the universe, he had transformed our understanding of reality. What had once been a small, finite cosmos was now a boundless, dynamic expanse. The psychological impact was enormous. Humanity was no longer at the center, no longer unique, but one tiny piece of a universe so large it defied comprehension. The ripple effects of Hubble's discovery are still felt today. His law of expansion remains one of the cornerstones of cosmology. His measurements open the door to questions about dark matter, dark energy, and the fate of the cosmos. But at the time, it was simply staggering enough to know that our galaxy was not the universe, but just one of billions. The universe had expanded overnight, not in physical size, but in human awareness, and with that expansion came a new kind of humility. Every generation before Hubble had thought they understood the cosmos, and every generation had been wrong. His work proved that the universe is always larger, stranger, and more mysterious than we expect. Looking back, Hubble's discovery feels like the moment when humanity truly entered the cosmic stage. Galileo showed us that Earth was not the center. Copernicus showed us that the Sun was just one star among many. But Hubble showed us the truth that dwarfed all previous revelations, that even our galaxy, with its sweeping spiral arms and billions of stars, was small, that we are surrounded not by empty darkness, but by a web of galaxies stretching as far as telescopes can see. And that beyond that horizon, there may be more still, an infinity that will forever remain beyond our grasp. In a sense, Hubble didn't just expand the universe, he expanded our imagination. And once the door to that ocean of galaxies was opened, it could never be closed again. For all the grandeur of galaxies and the brilliance of stars, one of the most unsettling truths about the universe is not how much there is, but how little. Space, at its heart, is defined not by abundance but by emptiness. The distances between celestial bodies are so vast, so unbridgeable, that the mind struggles to hold them. And if Hubble had given humanity the gift of realizing how many galaxies fill the skies, the next revelation was that those galaxies are separated by gulfs of unimaginable void. To measure that emptiness required a new set of tools, ones that could detect not what was there, but the yawning nothingness in between. The earliest step into this abyss came with parallax, a method so simple it seems almost laughable today. But at the time it was revolutionary. Imagine holding out your finger and closing one eye, then switching to the other. Your finger seems to shift position against the background. The same trick works with stars, except instead of switching eyes, astronomers use Earth's orbit around the Sun. By observing a star in January, then again in July, its position shifts ever so slightly against the distant background. That shift, parallax, was the first reliable way to measure the true distances to stars. In 1838, Friedrich Bessel used it to calculate the distance to 61 Cygni. The result was astonishing, 11 light-years, just 11. For the first time, humanity had measured a gap in space not in theories or guesses, but in raw numbers, and that number was crushing. 11 light-years doesn't sound enormous until you realize what it means. A light-year is nearly 6 trillion miles. 11 light-years is 66 trillion miles. And that was just to a nearby star, one of our closest neighbours. Bessel's calculation revealed not a cosy, crowded universe, but a staggeringly empty one. If our Sun were the size of a marble, 61 Cygni would be another marble nearly 800 miles away. The void between was incomprehensible. The universe was not a cluster of lanterns hanging just beyond reach, but an ocean of isolated lights drowning in vast seas of nothing. This revelation was as unsettling as it was profound. The stars twinkling overhead had always given comfort, a sense of closeness, but now that closeness was shattered. Every star was a solitary island in a sea of black, separated from its neighbours by gulfs wider than anything imaginable. And if the nearest stars were that far apart, what about the galaxies Hubble had just proven? If the Milky Way was just one among billions, then the emptiness between galaxies must be greater still. Humanity was beginning to grasp not only the immensity of the cosmos, but the terrifying loneliness of it. Parallax worked beautifully for nearby stars, but it quickly hit a wall. Beyond a few hundred light years, the shifts became too small to detect. The universe, it seemed, had locked most of its depth away. To push further, astronomers needed something more powerful, and Leavitt's Cepheids provided it. By measuring variable stars in distant galaxies, they could stretch their ruler across millions of light years. And what they found was even more humbling. Galaxies weren't just far. They were staggeringly far, and in between them lay voids so vast that entire civilizations, even if they existed, might never cross them. To put it in perspective, our Milky Way is about 100,000 light-years across. Andromeda, our nearest neighbour, is over 2.5 million light-years away. Imagine two glowing cities in the night, each filled with billions of stars separated by a dark desert 25 times wider than either of them. That desert is almost entirely empty. A few lonely stars drift in the intergalactic void, perhaps flung there by collisions, but otherwise there is nothing. The universe is not a crowded ballroom. It is a cavern where the lights are scattered thinly, each glowing faintly against an overwhelming dark. The scale of emptiness becomes even more staggering when you consider the large-scale structure of the cosmos. Galaxies are not scattered evenly. They cluster together in groups and superclusters, bound by gravity into great webs. But between those webs lie voids, enormous regions tens or even hundreds of millions of light-years across containing almost nothing. One of the largest known is the Bhuta's Void, a cosmic bubble 330 million light-years wide with only a handful of galaxies inside it. To cross it at the speed of light would take longer than humans have walked the Earth. It is emptiness on a scale so large that language begins to fail. And yet, this emptiness is not wasted space. It shapes everything. The gaps between galaxies are the reason galaxies survive at all. If the universe were crowded, stars would constantly collide, planets would be shredded, and life would have no chance to form. Emptiness is the stage that allows the few lights to shine. It is the canvas upon which the cosmic web is painted, the silence that gives meaning to the song of the stars. The universe, it turns out, is defined less by what is there than by what isn't. For astronomers, measuring emptiness became as important as measuring matter. By mapping voids, they could see how galaxies cluster, how dark matter scaffolds the universe, and how dark energy pushes everything apart. Each measurement confirmed that most of the cosmos is not stars, not planets, not galaxies, but emptiness. A cold, indifferent silence stretching in every direction. And yet, within that silence, the few sparks of light become all the more precious. For ordinary people, the realization of emptiness can be dizzying. The night sky, once comforting, now feels alien. Every star is impossibly far, every galaxy impossibly farther. It is not a friendly neighbourhood, but a wilderness so vast that human words can't capture it. But within that wilderness lies wonder. To know the distances is to know how extraordinary it is that we exist at all, that one small planet in one small corner of one galaxy can look out into that void and measure it. The emptiness may be overwhelming, but it also magnifies the miracle of presence. Hubble expanded the universe outward with galaxies. Parallax and Cepheids revealed the chasms between them. Together they showed us not only the size of the universe, but its loneliness. The cosmos is not a crowded marketplace. It is a desert where oases of light glitter in impossible isolation. And yet, within that desert, we are here. The emptiness is terrifying, yes, but it is also liberating. It tells us that there is space for everything, that the universe is vast enough to hold mysteries beyond imagination. Measuring the empty didn't make the cosmos less, it made it infinite. For decades, astronomers looked at the earliest chapters of the universe through a foggy window. The Hubble Space Telescope gave us dazzling images of distant galaxies, but it was limited. It could only peer so far, and when it looked back toward the dawn of time, the faintest galaxies appeared as tiny smudges of light, almost ghosts of what they truly were. Scientists built models to fill in the gaps, theories of how galaxies formed slowly from clumps of gas and dust, how stars lit up gradually over hundreds of millions of years, and how black holes grew from the collapse of the first massive stars into monstrous giants, only after billions of years of cosmic evolution. The story seemed neat, almost inevitable. Then came the James Webb Space Telescope, and within months of its first images, that story began to unravel. Launched in December 2021 and positioned 1 million miles from Earth, Webb was designed to do what Hubble couldn't: look into the infrared, the stretched-out light from the most ancient galaxies. Its mirrors were polished with unimaginable precision, its instruments chilled to near absolute zero, all so it could collect the faintest whispers of light from the universe's earliest years. And when Webb opened its golden eye, what it saw shocked everyone. Galaxies that shouldn't exist were staring back at us. Fully formed galaxies, rich in stars, some even with complex shapes, were appearing only 290 million years after the Big Bang. According to our models, there simply hadn't been enough time for such structures to emerge. The first galaxies were supposed to be tiny, chaotic clumps of stars, growing slowly over hundreds of millions of years. But what Webb revealed looked more like the galaxies we see today: large, organized, and impossibly mature for their age. This wasn't just one anomaly. Webb kept finding more. Galaxy after galaxy appeared earlier, brighter and more massive than expected. Some were 10 times larger than the models predicted could exist so soon after the universe began. And nestled inside them were black holes so enormous that they defied explanation. According to conventional physics, black holes grow slowly, feeding on stars and gas over billions of years. Yet Webb found supermassive black holes, millions or even billions of times the mass of our Sun, already in place just a few 100 million years after the Big Bang. It was like walking into a nursery and finding full-grown adults. Something was wrong with our understanding of cosmic evolution, and Webb was exposing it in brutal detail. Scientists scrambled to explain the data. Some suggested that perhaps stars formed more efficiently in the early universe than we thought, collapsing from pristine hydrogen clouds in great bursts. Others proposed that dark matter played a more active role, creating gravitational wells that allowed galaxies to assemble faster. A few even argued that we might be missing something fundamental about how physics works on cosmic scales, that the very laws we rely on may not hold in the same way near the universe's beginning. The debates were fierce, and they remain unresolved. But the message was clear. The universe wasn't following the rules we thought it did. For the public, the revelations were electrifying. Webb's images weren't just scientific, they were breathtakingly beautiful. Deep fields filled with galaxies of every shape and colour, stretching into what seemed like infinity. Each glowing smudge was a city of stars, each one existing when the universe was in its infancy. People looked at those images and felt the same mixture of awe and disorientation that scientists did. It wasn't just that the universe was bigger than we imagined, it was that it was more complex, more structured, and more ancient in its organisation than our theories could account for. Webb wasn't just a telescope, it was a time machine, and the past it revealed was far stranger than anyone expected. The discovery of early galaxies also raised haunting questions about our own. If galaxies could form so quickly, then perhaps the Milky Way story was not as typical as we thought. Maybe galaxies like ours are just one version of many possible histories. Maybe the universe is more chaotic, more diverse than the neat model suggested. And if black holes could grow so large so early, what does that say about the engines that power galaxies? Are there processes we don't understand, hidden forces shaping the cosmos in ways invisible to us? Webb has forced us to admit that we may have been blind to the true mechanisms of creation. One of the most dramatic implications of Webb's findings is that we may have been underestimating the size of the observable universe itself. If galaxies exist earlier than expected, then the timeline we've drawn for the cosmos might be off. Some scientists even wonder if we've misunderstood the rate of expansion, or the behaviour of dark energy, the mysterious force driving that expansion. The so-called Hubble tension, the conflict between different measurements of the universe's growth, suddenly looks even more urgent. Webb hasn't just shown us galaxies, It has reopened fundamental questions about the fabric of reality. And yet, there's something almost poetic about these surprises. Every time humanity has thought it understood the cosmos, reality has proven larger, stranger, and more complicated. The ancients thought the stars were lanterns on a dome. Centuries later, we thought the Milky Way was the entire universe. Hubble shattered that illusion with billions of galaxies. Now Webb is showing us that even our modern models are fragile, built on assumptions that can collapse with a single new image. It is a reminder that knowledge is always provisional, always waiting to be overturned by the next discovery. For astronomers, Webb's surprises are not discouraging but exhilarating. Science thrives on mystery, and the early universe has suddenly become the biggest mystery of all. Instead of confirming our neat theories, Webb has handed us a puzzle. How could so much complexity arise so quickly? The search for answers will fuel research for decades, drive new missions, and inspire a new generation of scientists to look deeper. What seemed like a settled story, the slow rise of galaxies over billions of years, has become a cliffhanger with no clear ending. For the rest of us, the lesson is more personal. The James Webb Space Telescope is showing us that the universe is not static, not predictable, but alive with surprises. It is bigger, faster, and stranger than our minds can fully grasp. And just as every generation before us had to admit they were wrong, we may someday look back at our own models with the same mix of awe and amusement. What Webb proves, more than anything, is that the universe is not finished revealing itself. There are secrets still hidden in the light of ancient stars, waiting to be uncovered. And if galaxies and black holes can defy the rules so early in cosmic history, then what else might we discover as we look deeper? The James Webb surprise is not the end of a story, but the beginning of a new one. It reminds us that the cosmos is not a solved puzzle, but an endless mystery, unfolding piece by piece. And if what we've seen so far is any indication, the universe is far stranger, far more dynamic, and far more extraordinary than we ever dared to believe. One of the strangest facts about the universe is that it's too big. Not just big in the sense of scale, but big in a way that seems to break the very rules of physics. We're told the cosmos is 13.8 billion years old, and yet the radius of the observable universe stretches out to about 46 billion light-years. On the surface, that makes no sense. If light can only travel 1 light-year per year, and the universe has existed for 13.8 billion years, then the farthest we should ever be able to see is 13.8 billion light-years away. And yet, when astronomers measure, they find galaxies at the edge of visibility sitting more than 3 times farther out. This isn't just a technical detail, it's a paradox that forces us to question how reality itself operates. The key to this puzzle lies in cosmic expansion. Space isn't static. It isn't a fixed stage upon which matter plays out its drama. Instead, space itself is stretching, pulling galaxies away from one another like dots on the surface of an inflating balloon. When we look at a distant galaxy, we aren't just seeing where it is now. We're seeing where it was billions of years ago when its light first left. In the time that light has been travelling toward us, space has continued to expand, dragging that galaxy even farther away. The result is that we can see galaxies that are at this moment 46 billion light-years from us, even though their light has only been travelling for 13.8 billion years. We're peering into the past while the present races ahead, and the result is a cosmos that feels like it's cheating the rules of time and distance. The expansion itself is strange enough, but what makes it even more unsettling is that it isn't slowing down. Common sense says gravity should tug everything back together. If you toss a ball into the air, Earth's gravity eventually pulls it down. By the same logic, the galaxies rushing apart after the Big Bang should gradually slow, maybe even collapse back in a big crunch. For decades, scientists expected to measure a cosmic deceleration. Instead, they found the opposite. In 1998, 2 teams studying distant supernovae discovered that expansion is accelerating. Something invisible, something unknown, is pushing galaxies apart faster and faster, stretching space at an ever-increasing pace. This force was given a name, dark energy. But the name is a placeholder, a confession of ignorance. We don't know what it is, why it exists, or how it works. We only know that without it, the universe makes no sense. The accelerating expansion has bizarre consequences. It means that more and more of the universe is slipping away from us forever. Galaxies beyond a certain distance are receding faster than the speed of light, not because they're moving through space, but because space itself is expanding faster than light can cross it. Those galaxies are already lost to us. Their light will never reach Earth, no matter how long we wait. The observable universe is like a shrinking island, with the shores pulling back faster than we can run. One by one, galaxies vanish beyond the horizon, not because they've stopped shining, but because expansion has carried them out of sight. Someday, trillions of years from now, observers in the Milky Way may look up and see only their own galaxy, isolated in an endless black void, unaware that billions of others ever existed. Even now, the numbers strain the imagination. The most distant galaxy we've detected, GNZ 11, lies 13.4 billion light-years away in terms of look-back time, the time its light has travelled to reach us. But its current distance, thanks to expansion, is over 32 billion light-years. Other faint galaxies discovered by Webb lie even farther. It means that when we gaze at the edge of the universe, we are looking at objects that no longer exist in the form we see them. They've been carried away, reshaped, maybe even destroyed, while their ancient light makes its final journey to us. We're not looking at what is. We're looking at what was, ghost images projected across time. The deeper we look, the less real our picture becomes. This distortion challenges our very perception of reality. If what we see in the sky is a frozen past, then the present universe, the real, living cosmos, is something we can never access. We're surrounded by illusions, fossils of light from long-dead stars and galaxies, and yet those illusions are all we have. The cosmos is like a hall of mirrors, reflecting images that no longer exist, and we are trapped inside trying to reconstruct a reality that's always slipping out of reach. The paradoxes don't stop there. Expansion also raises questions about the ultimate fate of the universe. If it continues accelerating, galaxies will drift so far apart that even their light won't connect. Stars will burn out, planets will freeze, and the universe will end not with a bang, but with a fade into darkness. A scenario called the heat death. But if dark energy changes its behavior, if it grows stronger over time, then expansion could eventually tear galaxies, stars, and even atoms apart in a catastrophic big rip. In either case, the logic of expansion leads to unsettling conclusions. The universe is temporary, and its vastness does not guarantee permanence. For scientists, these paradoxes are exhilarating. They point to gaps in our understanding, opportunities for discovery. But for the rest of us, they are humbling. To live in a universe where distances break the rules, where galaxies recede faster than light, where the present is forever hidden, is to confront the limits of human knowledge. It's a reminder that we are small, fragile creatures trying to make sense of forces so vast and alien that they defy comprehension. And yet, the very act of measuring them, of grappling with their contradictions, is extraordinary. We may not fully understand expansion, but we can see it, quantify it, and wrestle with its implications. That in itself is a kind of victory. The story of cosmic expansion is the story of a universe that refuses to fit inside human logic. It is bigger than time, faster than light, stranger than imagination. And the more we measure, the stranger it becomes. Every galaxy at the edge of vision is a reminder that we are staring at a mirage, a fleeting echo of a universe that has already changed. The expansion doesn't just stretch space, it stretches our minds, forcing us to accept that the cosmos is not bound by rules that feel comfortable. It is a place where distances lie, where horizons vanish, and where the very fabric of reality is slipping through our fingers. And yet, within that strangeness lies beauty. To know that the universe expands is to know that it is alive, dynamic, and in motion. It's not a static stage, but a story unfolding, one that began with the Big Bang and continues every moment. The paradoxes don't diminish the cosmos, they elevate it, reminding us that mystery is not a flaw but a feature. The universe is not meant to be easy to understand. It is meant to astonish, to humble, to stretch our minds as far as its galaxies stretch through space. When Edwin Hubble first discovered that the universe was expanding, he gave scientists not only a revelation but also a puzzle. His measurements suggested a certain rate of expansion, a number that would later be called the Hubble constant. In theory, it should have been simple. Measure the speed at which galaxies are moving away from us, compare it to their distances, and you can calculate the rate of expansion. That number is one of the most important in all of cosmology, because it not only tells us how fast the universe is growing, but also allows us to estimate its age, its size, and even its fate. But the Hubble constant has never been simple. From the very beginning, different methods gave different answers, and instead of converging as our instruments improved, the numbers have drifted farther apart. Today, nearly a century after Hubble's discovery, scientists are facing what they call the Hubble tension, a conflict so severe that it may hint at new physics, or even a complete revision of our understanding of the universe. The problem lies in how we measure the universe's expansion. One approach looks at the nearby cosmos, using what astronomers call the cosmic distance ladder. This ladder begins with relatively close objects whose distances we can measure directly, like Cepheid variables or Type-Ia supernovae. These serve as standard candles, predictable enough to use as markers. By comparing their true brightness with their observed brightness, astronomers can determine how far away they are, then combine that with the redshift of their galaxies to calculate how fast the universe is expanding locally. This method, refined over decades with Hubble and now the James Webb Space Telescope, gives a value for the Hubble constant of about 73 kilometers per second per megaparsec. In simple terms, that means for every 3.26 million light-years of distance, galaxies are receding 73 kilometers faster. But there's another way to measure the expansion, and it looks not at the local universe but at the earliest possible light. The cosmic microwave background, the faint afterglow of the Big Bang itself. Satellites like WMAP and Planck have mapped this radiation in extraordinary detail. By studying tiny fluctuations in the CMB, scientists can infer the conditions of the early universe and use the laws of physics to extrapolate forward, predicting how fast the universe should be expanding today. This method consistently produces a smaller value, about 67 kilometers per second per megaparsec. The difference may not sound like much, but in cosmology it is massive, a gulf that cannot be explained by measurement error. Both methods are precise to within less than 1%, and yet they disagree by more than 10%. This is the Hubble tension. It is not a minor discrepancy. It is a clash at the very heart of cosmology. If the local measurements are correct, then the universe is younger than the cosmic microwave background suggests. If the CMB-based predictions are correct, then our distance ladder is flawed in a way that generations of refinements have somehow failed to fix. The tension refuses to go away. With each new telescope, with each new dataset, the numbers become more precise, but they remain just as far apart. It's like measuring the same road with two rulers and always coming up short no matter how carefully you check. The implications are staggering. Some scientists suggest that new physics may be required to explain the discrepancy. Perhaps dark energy isn't constant but changes over time, altering the rate of expansion. Perhaps dark matter has strange properties we don't yet understand. Perhaps there are hidden particles, undiscovered forces, or cracks in Einstein's theory of general relativity itself. Others argue that we may be missing something in our models of the early universe, or that our assumptions about the behavior of light, matter, and gravity on cosmic scales are incomplete. The Hubble tension has become one of the most important problems in astrophysics, not because it is unsolvable, but because it suggests that the universe is hiding something fundamental from us. For the public, the Hubble tension is a reminder of how provisional science really is. For years, textbooks declared the universe's age as about 13.8 billion years. But if the local measurements are right, the universe might be hundreds of millions of years younger. Suddenly one of the most basic facts we thought we knew is back on the table. The very timeline of cosmic history, when stars first formed, when galaxies assembled, when black holes grew, might have to be rewritten. It's as if we thought we had drawn the outline of the universe, only to find that the edges don't match. The drama of the Hubble tension has only grown sharper with the James Webb Space Telescope. Webb's ability to see farther and with greater precision has confirmed the local measurements, strengthening the higher number for the Hubble constant. Yet Planck's map of the CMB remains unchallenged, holding firm to the lower number. Instead of resolving the tension, Webb has deepened it, forcing scientists to confront the possibility that both methods are correct within their own domains. but that something is missing in the bridge between them. This has fueled speculation that the universe may have gone through different phases of expansion. Maybe it expanded faster in its early years, then slowed, then sped up again due to dark energy. Maybe the rules themselves shifted in ways we don't understand. Some theorists propose the existence of exotic particles, early dark energy, that briefly altered the expansion rate in the young universe. Others imagine modifications to gravity itself, tweaks to Einstein's equations that only become noticeable on cosmic scales. None of these ideas are proven, but the very fact that they are being considered shows how disruptive the Hubble tension has become. For scientists, the tension is both a crisis and an opportunity. Crises in physics often precede revolutions. The ultraviolet catastrophe led to quantum mechanics. The precession of Mercury's orbit led to general relativity. The Hubble tension could be the crack that reveals the next great leap, the doorway to a deeper understanding of the universe. For now, it remains unsolved, a stubborn reminder that reality is not obliged to fit our neat theories, and for the rest of us, it is a story of humility. We live in an age of powerful telescopes, supercomputers, and precision measurements, yet the universe still refuses to give up its secrets. We can map galaxies billions of light-years away, detect ripples in space-time itself, and measure the afterglow of the Big Bang, but we cannot agree on how fast the cosmos is expanding. It is as if the universe is reminding us that knowledge is never final, that there are always mysteries waiting just beyond the horizon. The Hubble tension may one day be resolved with a new particle, a new theory, or a new measurement. Or it may linger, a thorn in the side of cosmology for generations. Either way, it teaches us something profound, that science is not a finished book, but a living story, full of conflict, revision, and surprise. The universe is larger, stranger, and more elusive than we can imagine, and sometimes the numbers themselves are the biggest mystery of all. When scientists first discovered that the universe was expanding, they assumed gravity would be the great equalizer. Galaxies might rush apart after the Big Bang, but the mutual pull of their mass would slow that expansion over time. Some even thought the universe might collapse back on itself in a cosmic rebirth. Then, in 1998, two independent teams studying distant supernovae made a discovery so shocking it rewrote everything we thought we knew. Instead of slowing, the expansion was accelerating. Galaxies weren't just drifting apart, they were being flung away from one another faster and faster, as if some invisible hand were pushing them. To account for this, scientists gave the mystery a name: dark energy. It was a placeholder, a label for something we could measure in its effects but not in its essence. And as the decades rolled on, the mystery only deepened. Today, dark energy is thought to make up nearly 70% of the entire universe. That means that everything we see, the galaxies, the stars, the planets, even all the dark matter is less than a third of reality. The rest is this ghostly, undetectable force, stretching space itself at an accelerating pace. Yet for all its dominance, we don't know what it is. It might be a property of space itself, what Einstein once called the cosmological constant, an energy woven into the very fabric of the vacuum. It might be some exotic new field, dynamic and shifting, with properties that change over time. Or it could be evidence that our fundamental understanding of gravity is incomplete. Each possibility is revolutionary, and each one comes with staggering implications. If dark energy is a constant, then the universe will expand forever, galaxies drifting into darkness until only isolated islands remain. If it is dynamic, its behavior could evolve, speeding expansion further or perhaps slowing it in ways we cannot yet predict. And if our equations of gravity need rewriting, then the very framework of physics, the laws that govern everything from falling apples to orbiting planets to collapsing stars, may be incomplete. The unsettling part is that, for all our progress, we are no closer to knowing which of these possibilities is true. Dark energy is everywhere, dictating the fate of the cosmos, yet it remains invisible, intangible, and unsolved. The search to uncover its nature has driven some of the most ambitious projects in modern science. Surveys of distant galaxies, like the Dark Energy Survey and Euclid, map how clusters of galaxies grow and shift under its influence. Observations of supernovae try to refine how expansion has changed across cosmic history. Experiments probe the cosmic microwave background. hoping to detect subtle fingerprints of dark energy in the early universe. Yet every effort so far has confirmed the same haunting result. Dark energy exists, it dominates, and it is utterly mysterious. For scientists, the frustration is profound. It is one thing to confront a mystery that lies at the edges of measurement, like the interiors of black holes. It is another to face a mystery that permeates everything, shaping the cosmos on the larger scales, yet defying all attempts to pin it down. Dark energy is not rare or exotic. It is the majority of the universe, and yet we cannot touch it, detect it, or even describe it beyond its effect of accelerating expansion. It is as if the universe is taunting us, hiding its most important feature in plain sight. The philosophical implications are equally unsettling. For centuries, humanity has believed that knowledge progresses steadily, peeling back layers of ignorance. But dark energy suggests that even with our most advanced instruments, there are truths that may remain forever beyond our grasp. We can describe what the universe does, but not why it does it. We can measure the effects, but the cause remains in shadow. It is a reminder that the cosmos is not obliged to be knowable, that some mysteries may be baked into the very structure of existence. And yet, in that uncertainty, there is also wonder. Dark energy forces us to rethink everything we thought we knew. It keeps science alive, keeps curiosity burning. If it turns out to be a cosmological constant, then space itself is alive with energy, a seething sea of potential that fills every void. If it is a new field, then we are on the verge of discovering a whole new layer of physics, perhaps tied to the elusive theory of everything that unites quantum mechanics and relativity. And if gravity itself must be rewritten, then we may be standing at the threshold of a revolution as profound as Einstein's a century ago. For ordinary people, dark energy can feel overwhelming. It means that most of the universe is invisible, unknowable, and utterly alien. It challenges the comforting notion that we live in a universe we can eventually map and understand. Instead, it suggests that reality is built on foundations we cannot yet see. But it also adds a strange kind of beauty. To live in a universe where 70% is mystery is to live in a universe that is alive with possibilities. We are surrounded by the unknown, and that unknown is not empty. It is dynamic, powerful, and essential. The dark energy problem is not just a scientific puzzle. It is a reminder of how small we are, how much lies beyond our reach. It humbles us, but it also inspires us. Every time we look deeper, the universe grows stranger, larger, and more astonishing. Dark energy is the latest and perhaps the greatest reminder that we are not at the center of understanding. We are explorers at the edge of an endless frontier, staring into the dark and daring to ask what lies within it. And perhaps that is the true power of dark energy, not just in shaping galaxies or dictating the fate of the cosmos, but in shaping us, our curiosity, our drive to explore, our refusal to accept ignorance as final. The universe may never reveal its deepest secrets, but the act of chasing them gives our tiny lives a connection to the vastness. In a cosmos where emptiness dominates, where light itself fades, it is the mystery that keeps us alive with wonder. If dark energy is the ghostly hand pushing the universe apart, then dark matter is the hidden glue holding it together. For decades, astronomers assumed the stars we saw in galaxies told the whole story, that the light revealed the mass. But when scientists measured how galaxies actually moved, they found something that made no sense. Stars at the edges of galaxies were orbiting far too quickly, moving at speeds that should have flung them into intergalactic space. The visible matter, stars, planets, gas clouds, simply didn't have enough gravity to hold them in place. According to the laws of physics, those galaxies should have been flying apart, and yet they weren't. Something unseen, something invisible, but immensely powerful was providing the missing gravity. That something became known as dark matter. The discovery began in the 1930s, when Fritz Zwicky studied the Coma cluster of galaxies. He measured how fast the galaxies were moving inside the cluster, and realized they were moving far too quickly to be bound together by the visible matter. He proposed that dunkel materie, dark matter, must be there, unseen but dominant. At the time, most dismissed it as speculative, but decades later, Vera Rubin confirmed the same effect within individual galaxies. She measured the rotation curves of spiral galaxies and found that instead of slowing down at the edges as expected, the stars maintained high velocities all the way out. The only explanation was that vast halos of invisible matter surrounded each galaxy, outweighing the visible stars by a factor of 5 or more. Rubin's work turned dark matter from a fringe idea into a central pillar of cosmology. Today, we believe that dark matter makes up about 27% of the universe, nearly 6 times more than all the ordinary matter we can see. Without it, galaxies couldn't exist. Their stars would disperse, their structures would dissolve, and cosmic webs of clusters and filaments would never have formed. Dark matter is the hidden scaffolding of the cosmos, shaping the large-scale structure of everything we observe. It's everywhere, passing through us every second, yet we cannot see it, touch it, or detect it directly. Its existence is inferred only from its gravitational fingerprints. The invisible hand that bends light shapes galaxies and anchors the universe. But what is it? That question has haunted physics for nearly a century. The leading candidates are exotic particles beyond the standard model of physics, things like WIMPs, weakly interacting massive particles, or axions, hypothetical particles so elusive they barely interact with normal matter at all. Huge underground detectors, buried in mines or submerged under mountains, have been built to catch a single flash of dark matter colliding with ordinary atoms. For decades these detectors have waited, sensitive enough to register even the faintest hint, but so far nothing definitive has appeared. The silence has been deafening. Some theorists argue that dark matter might not be particles at all, but something stranger. Perhaps it is primordial black holes, ancient remnants from the first moments of the Big Bang, too small to detect directly but massive enough to exert gravity. Perhaps it is a new form of matter we haven't even conceived, tied to dimensions beyond the ones we know. Or perhaps, most unsettling of all, dark matter isn't real, that what we call dark matter is actually evidence that our understanding of gravity is wrong. Modified Newtonian dynamics, or MOND, proposes that at galactic scales, gravity doesn't behave the way Einstein described, and that the missing mass is an illusion caused by flawed equations. But so far, MOND struggles to explain the full range of observations, while dark matter remains the simpler if unsolved explanation. The mystery deepens when we look at the cosmic web. Simulations of the universe, with dark matter included, produce filaments and clusters that look remarkably like what we observe through telescopes. Remove dark matter from the equations, and the universe falls apart, galaxies fail to form, and cosmic structure collapses. In that sense, dark matter is one of the most successful ideas in cosmology. Without it, nothing works. And yet, its refusal to show itself directly is maddening. It is as if we are looking at the shadow of a creature we cannot see, a presence that shapes everything while remaining forever hidden. Gravitational lensing provides another eerie confirmation. When light from a distant galaxy passes near a massive cluster, it bends, distorting the image like a funhouse mirror. By measuring the amount of bending, scientists can map the mass of the cluster, both visible and invisible. Over and over, these maps show vast quantities of unseen matter. In some cases, like the famous bullet cluster, the evidence becomes undeniable. Visible gas from colliding clusters separates from the invisible mass, which sails through unaffected. Dark matter reveals itself in the separation between light and gravity, a silent signature written across billions of light years. For ordinary people, the idea that most of the universe is made of something we cannot see is deeply unsettling. Every atom we've ever known, every star, every planet, every living thing, is just a sliver of reality. The rest is a hidden ocean, pressing in from all sides yet forever invisible. It challenges our sense of certainty, our belief that what we see is what exists. The truth is that our eyes, our telescopes, even our most advanced instruments capture only a fraction of reality. The universe is built on shadows, and we are left guessing at their shapes. Yet there is a strange comfort in the mystery. If dark matter holds galaxies together, then in some sense it holds us together too. Without it, the Milky Way would never have formed, and Earth would not exist. We owe our lives to something we cannot see, something that may forever elude detection. That is both terrifying and beautiful. Dark matter is not just a scientific puzzle, it is a reminder that the universe is deeper, richer, and stranger than human senses can grasp. The hunt continues. New detectors are being built, more sensitive than ever, searching for the faintest whispers of interaction. Particle accelerators smash protons together at near-light speeds, hoping to glimpse traces of exotic matter. Astronomical surveys map the universe with increasing precision, tracing the skeleton of dark matter across billions of light-years. Every failure to detect it is frustrating, but also exhilarating. Because when the answer comes, whatever it will rewrite physics. If we find the particles, we will finally understand the hidden majority of the cosmos. If we don't, then we may be forced to accept that our theories of gravity, of matter, of reality itself are incomplete. Either way, the dark matter mystery is not a dead end, it is a doorway. For now, we live in a universe where most of the matter is dark, where the visible is just the tip of an invisible iceberg. It is a humbling truth, but also a liberating one. It means that discovery is far from over, that the universe still holds secrets vast enough to astonish us. Dark matter is not just missing mass. It is the greatest riddle of existence, hiding in the shadows, waiting to be revealed, and when it finally steps into the light, the universe may never look the same again. If the universe itself wasn't strange enough, the latest frontier of cosmology takes us into territory that feels more like science fiction than science. It's the idea that our universe might not be the only one, that what we call reality could be just one bubble in a vast cosmic foam, one chapter in a book with infinite pages. This concept, known as the multiverse, has leapt from the fringes of speculation into the centre of scientific debate. It is controversial, unproven, and deeply unsettling. But if it's true, then the story of the cosmos is far larger and stranger than we ever imagined. The roots of the multiverse idea lie in cosmic inflation, the theory that the universe expanded faster than the speed of light in the first tiny fraction of a second after the Big Bang. This inflationary burst smoothed out the cosmos, explaining why the universe looks so uniform on large scales, while also planting the seeds of structure that later grew into galaxies and clusters. Inflation theory has been enormously successful in matching observations, but it comes with a bizarre consequence. Many models of inflation suggest it doesn't stop everywhere at once. Instead, it ends in some regions, creating bubble universes, while continuing in others. Our universe would be one such bubble, but there could be countless others, each with its own physics, its own laws, maybe even its own dimensions. This idea is called eternal inflation, and it implies a multiverse far beyond our reach. Another path to the multiverse comes from quantum mechanics. In the standard interpretation, the quantum world is governed by probabilities. A particle might be here or there, spin up or spin down until we measure it. But some interpretations, like the many worlds hypothesis, suggest that all outcomes actually happen. Every quantum event splits reality into branches, each equally real. If that's true, then there isn't one universe but an infinite number, with every possible version of history playing out somewhere. In one universe, you chose differently and your life went another way. In another, dinosaurs never went extinct. In another, Earth itself might not exist at all. It's a staggering vision, one where possibility itself becomes reality. String theory, a leading attempt to unify quantum mechanics and gravity, adds yet another layer. It predicts a vast landscape of possible universes, each with different physical constants, shaped by the way extra dimensions are compactified. Our universe might be just one configuration among trillions, chosen not because it is special, but because it is one of the few where the laws of physics allow stars, galaxies, and life to exist. This anthropic reasoning, that we find ourselves here because only in this kind of universe could we exist, has fueled both fascination and frustration. Some see it as the ultimate explanation, others as a retreat from science into speculation. What makes the multiverse idea so controversial is that it may be untestable. By definition, other universes would be beyond our cosmic horizon, forever out of reach. We cannot see them, measure them, or interact with them. For many scientists, that makes the multiverse philosophy rather than physics, but others argue that indirect evidence might be possible. Collisions between bubble universes could leave scars in the cosmic microwave background, faint imprints of encounters with realities beyond our own. Variations in fundamental constants, if detected, might hint at a wider landscape of universes, and the sheer success of inflation and string theory, even without direct proof, lends credibility to the idea that the multiverse may be real, even if we can never touch it. For ordinary people, the concept is both thrilling and disturbing. If there are infinite universes, then everything that can happen does happen somewhere. Every decision you make, every chance event, plays out in parallel realities. That means there could be versions of you living completely different lives, versions who succeeded where you failed, or failed where you succeeded. It challenges our sense of uniqueness, our belief that this reality is the only one. It raises profound philosophical questions. What does it mean to be you if infinite versions exist? Does choice matter in a multiverse, or is every path taken anyway? And yet, there is also something strangely comforting in the idea. If the multiverse exists, then the cosmos is not limited. It is infinite in possibility, richer than we can ever imagine. It suggests that reality itself is not a single fragile thread, but a vast tapestry, with countless variations woven together. Even if our universe ends someday in heat, death or collapse, others will go on spinning out new stories forever. The multiverse replaces cosmic finality with eternal renewal. For scientists, the multiverse is both a dream and a nightmare. On one hand, it could explain mysteries like the finely tuned values of physical constants. Why is gravity so weak compared to electromagnetism? Why does dark energy have the value it does, small enough to allow galaxies to form but large enough to drive expansion? In a multiverse, the answer is simple. Because we live in one of the universes where the conditions happen to allow observers. On the other hand, this explanation is unsatisfying, because it offers no testable predictions. If everything is possible, then nothing can be ruled out. Science thrives on falsifiability, and the multiverse seems to slip through that net. But perhaps the deeper lesson is that the universe, or multiverse, is not obliged to fit our standards of neatness. Reality may be messy, infinite, and forever beyond our full comprehension. That doesn't make it less real, it makes it more mysterious. The multiverse idea is a reminder that our current understanding is always provisional, always limited. 1,000 years ago, people thought the stars were holes in the sky. A century ago, they thought the Milky Way was the whole universe. Now we know there are billions of galaxies, and we are beginning to wonder if there are billions of universes. Each step expands our vision, and each step humbles us further. For storytellers and dreamers, the multiverse is irresistible. It fuels science fiction, philosophy, and imagination. It allows us to imagine worlds where history went differently, where civilizations rose and fell in alien patterns, where life evolved in forms we cannot conceive. And while the multiverse may never be proven, it has already reshaped how we think about reality. It has forced us to ask bigger questions, to stretch our minds beyond the comfort of a single universe. The multiverse possibility may never be settled. It may remain forever on the border between science and speculation, tantalizing but unreachable. But whether real or not, it changes us. It forces us to confront the limits of human knowledge, to accept that reality may be larger and stranger than we dare to believe. And in that confrontation, there is awe. Because even if there is only one universe, it is vast beyond comprehension. And if there are many, then the true scale of existence is infinite. Either way, we are left staring into a cosmos that refuses to be small, a reality that insists on being larger than our imagination. When we think of the universe, we tend to imagine it as scattered and chaotic, a random spread of stars and galaxies across an endless void. But in recent decades, astronomers have uncovered something astonishing. The cosmos has structure on scales so vast they almost break the laws of physics. These are not galaxies, not even clusters of galaxies, but superstructures that stretch across hundreds of millions or even billions of light years. They are so large that they challenge the very assumptions of cosmology, pushing against a principle that has guided science for generations, the cosmological principle, which states that on the larger scales the universe should look the same everywhere, with no preferred direction or pattern. These immense structures should not exist, and yet they do. One of the first great shocks came in 1989 with the discovery of the CF A2 Great Wall. Using data from the Center for Astrophysics Redshift Survey, astronomers mapped galaxies in 3 dimensions for the first time. What they found wasn't a random scatter, but a massive wall of galaxies stretching 500 million light-years long, 200 million light-years wide, and 15 million light-years thick. It was the largest known structure in the universe at the time, and it immediately raised eyebrows. According to cosmological theory, structures that large should take longer than the age of the universe to form. The Great Wall was an anomaly, a vast slab of matter stitched across the sky. Then came the Sloan Great Wall, discovered in 2003, even larger, 1.37 billion light-years in length. To grasp that scale, imagine lining up over 13,000 Milky Ways side by side. The sheer immensity seemed impossible. How could gravity pull matter into such coherent shapes across distances so vast? According to standard models, the largest cosmic structures should max out at around 1.2 billion light-years before the universe's expansion would tear them apart. The Sloan Great Wall pushed right up against that limit, straining the definition of what was even physically possible, but the discoveries didn't stop there. In 2013, astronomers identified the Hercules Corona Borealis Great Wall, a structure so vast it defies belief. Spanning over 10 billion light-years across, it is the largest known structure in the observable universe. To put that in perspective, the universe itself is 13.8 billion years old, and the observable universe stretches about 93 billion light-years in diameter. This single structure takes up 1/10 of that span. Its existence is a direct challenge to the cosmological principle, because it suggests the universe has patterns and clumps far larger than theory allows. If the cosmos is supposed to be homogeneous on large scales, then how can such titanic walls exist? Some scientists argue these superstructures may not be real structures at all, but statistical illusions, chance alignments of galaxies that only appear connected from our perspective. But even if that's true for some, the consistency of these findings is difficult to ignore. Cosmic filaments and walls keep showing up in surveys, woven into a vast cosmic web that stretches across the universe. The web itself is a network of dark matter filaments, with galaxies strung along them like beads on a string. Where the filaments intersect, clusters form. Where they spread out, voids emerge. This structure is visible in simulations and confirmed by observations, yet its largest manifestations, the wall spanning billions of light-years, still leave scientists uneasy. The problem is time. The universe is only 13.8 billion years old, and galaxies began forming a few 100 million years after the Big Bang. That means there's been a finite amount of time for gravity to pull matter together into structures. On smaller scales, this works perfectly. Clusters and superclusters fit the timeline. But when we leap to walls billions of light-years long, the math doesn't add up. Gravity shouldn't have had enough time to sculpt structures that large. Either the universe is older than we think, or our models of how matter clumps on cosmic scales are incomplete. Both possibilities are deeply unsettling. Some theories suggest that dark matter may be the culprit. If dark matter formed vast filaments in the early universe, it could have seeded the growth of structures more quickly than expected. Others point to dark energy, arguing that its behavior in the early cosmos may have allowed matter to cluster differently than our models predict. A few even propose that the cosmological principle itself may be flawed, that the universe is not uniform on the larger scales, but instead has directions, patterns, and anisotropies baked into its very fabric. If true, that would upend one of the cornerstones of modern cosmology. The scale of these structures also raises haunting questions about what lies beyond the observable universe. If we can detect walls stretching billions of light-years within our horizon, what might exist outside it? Are there even larger structures, cosmic features so vast we cannot comprehend them? The thought is dizzying. Perhaps our observable universe, enormous as it seems, is just a tiny patch of a far grander cosmic architecture, one with features so immense they dwarf even the Hercules Corona Borealis Great Wall. For ordinary people, the discovery of these structures is both awe-inspiring and terrifying. It forces us to confront scales so vast they are almost meaningless. 1 billion light-years is not just a number. It's a distance light itself takes 1 billion years to travel, and yet here we see walls of galaxies stretching across 10 billion. It makes our own galaxy, our own solar system, our own lives feel vanishingly small. but it also fills the mind with wonder. To exist in a universe where such colossal structures form is to live in a reality beyond imagination, a reality that refuses to be simple or tame. For scientists, these discoveries are not just curiosities but challenges. They push against the boundaries of theory, demanding new models, new physics, or new interpretations. They remind us that the universe is not finished surprising us, that even on the grandest scales there are mysteries waiting to be unravelled. The cosmic web is not just a map of matter, it is a map of our ignorance, tracing the outlines of questions we have yet to answer. In the end, the discovery of cosmic structures too big to exist is a humbling reminder that the universe is not bound by our expectations. We create models, run simulations, and believe we have captured its logic, but then it reveals something that defies our rules. The great walls, the filaments, the webs, they are the universe's way of telling us that it is stranger, larger, and more complex than we dare to believe. And as our telescopes grow stronger, as our surveys map deeper, we may find that these titanic structures are only the beginning, the first hints of a cosmic architecture so vast that it makes even the grandest human imagination seem small. If the universe had a beginning, then it must also have an end. That simple logic has haunted cosmology ever since the discovery of the Big Bang, because it forces us to confront not only where everything came from, but where everything is going. The question is not just academic. It cuts to the heart of existence itself. Are we living in a cosmos that will collapse in fire, fade into silence, or tear itself apart in violence? The answer depends on forces we barely understand, and the theories scientists have proposed range from chilling inevitabilities to mind-bending possibilities. For much of the 20th century, the leading idea was the Big Crunch. If the gravitational pull of all the matter in the universe was strong enough, then expansion would eventually slow, stop, and reverse. Galaxies would halt their drift, then fall back together, colliding in a fiery collapse. Stars would ignite in bursts of destruction. Black holes would merge into titanic monsters, and finally all matter would be compressed into a single dense point, perhaps triggering another Big Bang. In this vision, the universe is cyclical, an endless heartbeat of creation and destruction. The thought carries a certain symmetry, a poetic rhythm of beginnings and endings, but as evidence for accelerating expansion mounted, the Big Crunch faded into the background. Unless dark energy behaves in a radically unexpected way, the pull of gravity will never overcome it. The universe is not slowing, it is speeding up. That acceleration leads to the most widely accepted scenario today, the heat death of the universe. In this vision, expansion continues forever, stretching galaxies farther and farther apart until they vanish from one another's horizons. Stars will exhaust their fuel, burning out into white dwarfs, neutron stars, and black holes. Over trillions of years, even these remnants will fade as black holes slowly evaporate through Hawking radiation. In the end, the cosmos becomes a dark, cold, and empty place, a thin soup of particles drifting in endless night. No light, no warmth, no structure, just entropy. It is not a violent end, but a slow dissolution, the extinguishing of every spark. The universe dies not with a bang, but with a whisper. And yet there are other possibilities, each more unsettling than the last. One of the most terrifying is the Big Rip. If dark energy is not constant but grows stronger over time, it could accelerate expansion to catastrophic levels. First, galaxies would be torn away from one another, then stars would be ripped from galaxies, planets from stars. Eventually, the expansion would overcome even atomic forces, tearing atoms themselves apart. In this scenario, the very fabric of matter disintegrates, leaving nothing but shredded space-time. The Big Rip could occur trillions of years in the future, or, if dark energy behaves more aggressively than we think, far sooner. The uncertainty itself is frightening, because it suggests we may be living in a cosmos that is fundamentally unstable. Another possibility is vacuum decay, an end born not from expansion but from quantum physics. The Higgs field, which gives particles their mass, may not be in its lowest possible state. If it is in a false vacuum, then a bubble of true vacuum could someday form, expanding at the speed of light and rewriting the laws of physics as it spreads. Inside that bubble, atoms would disintegrate, chemistry would cease, and reality as we know it would vanish in an instant. There would be no warning, no defense. just the sudden annihilation of everything. Though this scenario is speculative, the mathematics behind it is consistent with what we know. It is a reminder that the stability of the cosmos may rest on fragile foundations, a cosmic balance that could topple without notice. Some theories imagine more exotic fates. In one, the universe tunnels into another state, birthing new dimensions or collapsing into a higher-order reality. In another, black holes dominate the future, merging into one final supermassive entity before evaporating over unimaginable timescales. Some cosmologists even argue for cyclical models, where the universe bounces back from death into rebirth, a cosmic phoenix rising endlessly from its ashes. In these models, the Big Bang was not unique but one of many, and our universe may be just the latest in an infinite series. Such ideas are speculative, but they highlight a truth that runs through all the theories. The end of the universe will be stranger than anything we can picture. For ordinary people, these visions are almost impossible to comprehend. What does it mean to imagine time stretching trillions of years into the future, long after every star has died? What does it mean to think of reality itself unravelling in an instant, or of new universes being born from the collapse of this one? The sheer scale of these endings dwarfs human imagination. They force us to confront our smallness, not just in space but in time. Our entire history, from the first spark of life to the last word ever spoken, is a flicker against the backdrop of cosmic fate. And yet, there is also wonder in these possibilities. To live in a universe that will one day die is to live in a universe that is alive now. The stars we see, the galaxies that shine, the very fact of existence, all of it is fleeting, temporary, and therefore precious. Knowing the cosmos has an end doesn't diminish its beauty. It magnifies it. Every moment becomes more miraculous against the certainty of eventual silence. For scientists, the study of cosmic endings is not just about doom, but about understanding. Each scenario depends on the behaviour of dark energy, dark matter, and the fundamental laws of physics. By probing the fate of the universe, we probe its nature, testing the very foundations of reality. The end becomes a laboratory for the beginning, a way of asking not only where we are going, but where we came from. Perhaps that is the deepest truth hidden in these theories. The universe is not a static place, but a story, with a beginning, a middle, and an end. We are part of that story, a brief chapter in a cosmic epic that stretches across billions of years. To ask how it ends is to ask what kind of story we are living in, one of rebirth, one of silence, or one of unimaginable transformation. Whatever the answer, it is a story far larger than us, yet one in which we play our small fleeting role. In the end, the question of cosmic death is less about fear than perspective. Whether the universe collapses, fades, rips, or tunnels away, the fact remains that we are here now, alive in a cosmos vast enough to dream of its own endings, and perhaps that is the greatest miracle, that the universe in all its immensity gave rise to creatures capable of wondering how it will die. No matter how powerful our telescopes become, no matter how far technology advances, there is a limit we cannot pass. The observable universe stretches out to 46 billion light-years in every direction, but beyond that lies an eternal mystery, a horizon we will never see across. This cosmic boundary is not made of matter, nor is it a wall in any physical sense. It is a horizon defined by time itself, the edge beyond which light has not had enough years to reach us. The expansion of the universe means that as space itself stretches, galaxies once within our view are carried farther away until their light can no longer bridge the gap. Beyond this horizon, there is more universe, perhaps most of the universe, but it is sealed from us forever. It is as though we are trapped inside a bubble, surrounded by a darkness that hides truths we can never uncover. This concept is difficult to grasp because it is not a matter of distance alone, but of time and expansion. Imagine standing on a beach, looking out to sea. The water stretches to the horizon, but you know it does not end there. There are ships, islands, continents beyond your sight, but no matter how sharp your eyes, you cannot see them. The universe works in a similar way, but with a cruel twist. Unlike a sea horizon, which can be crossed, the cosmic horizon is permanent. We can never move beyond it because space itself is expanding faster than light beyond that line. Galaxies there are receding so quickly that even if they emitted light now, it would never reach us. They are lost to us forever, vanishing over the edge of time itself. What lies beyond that horizon? That question gnaws at cosmologists, because the answer may contain truths about the very nature of existence. Our observable universe contains hundreds of billions of galaxies, but it could be only a tiny fraction of the whole. For all we know, the cosmos may be infinite, stretching endlessly in every direction, or it may be finite but unimaginably vast, curving back on itself like the surface of a sphere. Beyond the horizon may lie regions where galaxies are clustered in different ways, where the cosmic web takes on shapes we cannot imagine. It is even possible that the laws of physics themselves vary beyond our bubble, that constants we take for granted shift into new values, birthing realities that behave in ways alien to our own. There are tantalizing hints that the horizon might not be uniform. The cosmic microwave background, the faint afterglow of the Big Bang, shows subtle fluctuations, tiny differences in temperature across the sky. Some anomalies, like the so-called cold spot, have fueled speculation that they could be scars left from collisions with other universes, shadows cast across our bubble by realities beyond. While most scientists caution that these anomalies may simply be statistical noise, the possibility that the horizon itself holds fingerprints of something greater is almost irresistible. If true, the edge of what we can see is not just a barrier, but a clue, a message written in light from the first moments of time. For humanity, the horizon is both a limitation and an inspiration. On one hand, it is humbling to know that there are places we will never see, truths we will never know. No spacecraft, no telescope, no future civilization will ever pierce that boundary. Even if we mastered faster-than-light travel, the horizon is not a place to go. It is a speed limit written into the fabric of reality. The universe itself forbids us from seeing everything. And yet, that very impossibility fuels curiosity. Knowing there is more than we can ever touch forces us to ask questions more daring, to imagine possibilities more vast. The horizon is a wall, but it is also a challenge. The emotional weight of this truth is hard to overstate. For thousands of years, humans believed they could eventually understand everything, that the universe was a puzzle waiting to be solved. The cosmic horizon shatters that dream. It tells us that some answers are forever beyond us, not because we lack intelligence or tools, but because reality itself draws a line. There are galaxies whose light will never reach us, civilizations we will never know, structures we will never map. The majority of the universe is hidden behind that veil, and no effort will change it. It is a sobering reminder of how small we truly are, stranded in a bubble of light in an endless darkness. And yet, there is also a strange beauty in this limitation. Perhaps the fact that we cannot see everything makes what we can see more precious. The galaxies we observe, the cosmic web we map, the faint glow of the Big Bang, all of it is a gift, a fleeting glimpse through a narrow window. That window is temporary. As expansion accelerates, galaxies at the edge of visibility are slipping away forever. Billions of years from now, the observable universe will shrink, not grow, as distant galaxies disappear into the night. Future astronomers may see only the local group, a handful of galaxies adrift in darkness with no evidence of the wider cosmos. In that sense, we live at a privileged moment, a time when the universe is still visible in all its vastness. To be alive now, with the ability to see across billions of light years, is itself extraordinary. Some scientists take the horizon as evidence of something even more profound, that our universe is only one of many. If horizons are inevitable in expanding universes, then each bubble of space-time may be surrounded by countless others, each sealed off by its own horizon. We may be one bubble in an infinite foam, never able to see the others but shaped by their existence nonetheless. The horizon becomes not just a boundary but a doorway, a hint that our cosmos is part of something even greater. For ordinary people, the idea of an unreachable edge can be unsettling. We crave certainty, closure, a sense that the universe is knowable. The horizon denies us that comfort. It insists that mystery is permanent, that no matter how far we reach, the unknown will always outpace us. And yet, this may be the greatest lesson of all. The universe is not designed to be solved. It is designed to inspire awe, to humble us, to keep us searching even when answers slip away. The horizon we cannot cross is not just a scientific concept, it is a metaphor for human existence. We are finite beings in an infinite reality, able to glimpse only part of the whole. But that glimpse is enough to change us, to make us question, wonder, and dream. The edge of the universe is the edge of knowledge, and standing at that edge, we are reminded that mystery is not a failure of science, but its very fuel. The horizon may be permanent, but so is curiosity. After everything we've uncovered about the cosmos, the violent birth of stars, the silent force of dark matter, the strange repulsion of dark energy, the possibility of multiple universes, and the looming question of how it all ends, there remains one unavoidable truth. We are a part of it. Humanity, fragile and fleeting, exists within this infinite stage, and no matter how small our place may seem, we are bound to the same cosmic laws that govern galaxies and black holes. Section after section of discovery leads to this sobering yet exhilarating realization. The universe isn't just out there, it is in us. Our atoms were forged in ancient stars, our very breath carries the echoes of supernovae, and our thoughts are arranged by the same physical laws that shape the cosmic web. But what does this mean for us? Why does it matter that we live in a universe so vast it defies comprehension? The answer lies in the tension between insignificance and wonder. For centuries, humans believed themselves to be at the center of everything. The Earth was the hub, the heavens revolved around us, and creation was a stage built for humanity. That illusion has been shattered over and over. We are not the center of the solar system, nor the galaxy, nor the universe. Each discovery has pushed us farther from the spotlight, and yet, paradoxically, each discovery has also made us more extraordinary. Because in this endless cosmos, full of stars and voids, we are the ones asking questions. No galaxy wonders about its place. No black hole contemplates infinity. No superstructure of galaxies debates its future. Only we do. That makes us small in scale, but vast in meaning. The human mind has stretched far enough to imagine horizons it can never cross, and that act alone places us within the story of the universe in a unique and profound way. When we gaze into the night sky, we are not just looking at distant lights, we are looking back in time. Every star is a message from the past, every galaxy a fossil of ancient light. To see the universe is to see history written across space, and the most haunting part is knowing that the further we look, the more we approach the ultimate boundary, the horizon we cannot cross. Beyond it lies silence, but within it lies a record of nearly 14 billion years of cosmic drama. That window, however temporary, has given us a perspective no other known life form possesses. The cosmos has given us the tools to witness itself, and in doing so, it has made us part of its unfolding mystery. This realization carries both humility and responsibility. If life is rare, and we still don't know whether it is or not, then we may be among the only eyes the universe has to observe itself. Our curiosity is not just a personal trait, but a cosmic phenomenon, an emergent property of matter arranged in a way that can reflect upon itself. That thought alone reframes human existence. It suggests that our role is not dominance but witness, not control but understanding. Every discovery we make, every question we ask is part of the universe learning about itself through us. We are star stuff, yes, but we are also star thoughts, fleeting but luminous. And yet, the weight of that perspective can feel overwhelming. To know that the universe will go on long after we're gone, to imagine stars burning for billions of years while civilizations rise and fall in the blink of cosmic time, is to confront our own mortality on a scale that dwarfs imagination. Against such a backdrop, human life can feel meaningless, a dust speck on a cosmic shore. But perhaps meaning does not come from scale at all. Perhaps meaning comes from experience, from the act of being alive in a universe that does not need us but still allows us to exist. The very unlikeliness of it, the fact that atoms could assemble into consciousness on a small blue world, makes every moment a miracle. For science, this perspective is both grounding and motivating. We study the end of stars not just to know how they die, but to understand how they gave us life. We map cosmic webs not just to measure their size, but to see the skeleton upon which galaxies, and eventually planets, formed. Every measurement, every telescope image, every theory about dark matter or dark energy is not just an abstract puzzle. It is part of our attempt to locate ourselves within the whole. To know where we are, to know what we are, is one of the deepest human needs, The cosmos answers with scale and silence, but within that silence we find wonder. Some thinkers suggest that our role may go beyond mere observation. If civilizations survive long enough, perhaps they could influence the fate of the universe itself. Concepts like Dyson spheres or star lifting are attempts to stretch survival across astronomical timescales, while speculative ideas like universe engineering or creating baby universes suggest that intelligence could one day play a part in cosmic cycles. Whether these dreams are ever achievable is irrelevant. What matters is that we can imagine them. The fact that minds born of stardust can conceive of reshaping reality speaks to the audacity of human imagination. In a universe that may one day end in silence, imagination is our defiance. But even if our future is humble, even if humanity vanishes and Earth becomes just another forgotten planet, the fact remains that we were here. For a brief moment, the universe was aware of itself through us. That awareness cannot be undone. It is part of the cosmic story forever, woven into the history of one universe among perhaps many. In the end, our place in the infinite is not defined by how large we are, but by the fact that we exist at all. So, where does this leave us? We are tiny, yes, but we are also luminous. We are temporary, but in that brevity lies beauty. The stars will continue to burn, galaxies will continue to drift, dark matter will continue to shape the unseen scaffolding of reality. But for now, here, in this corner of the cosmos, we are alive, thinking, feeling, questioning. And that is enough. The human place in the infinite is not at the centre, not at the edge, but in the act of wonder itself. We belong not because the universe was made for us, but because we are made of it, and because through us it dares to know itself. For every mystery the universe allows us to solve, a dozen more appear in its place, and perhaps that is the most haunting truth of all. The questions will never end. We can build the most powerful telescopes, probe the earliest light, and model cosmic structures across billions of years, but the horizon of knowledge always retreats. No matter how far we push, there will always be a boundary we cannot cross, a puzzle we cannot complete, a layer of reality that refuses to be revealed. And yet, this endless cycle of discovery and uncertainty is not a flaw in our journey. It is the very engine of it. Without mystery, there is no curiosity. Without curiosity, there is no science. The universe hides its secrets not to mock us, but to ensure that wonder survives. Even the most basic questions remain unsettled. What sparked the Big Bang? Was it the birth of everything, or just a transition from a state we cannot yet conceive? If time itself began in that moment, what does it mean to ask what came before? These questions edge into philosophy, but they also sit at the heart of physics. If we ever uncover the true origins of the cosmos, the answer will almost certainly raise even deeper questions, forcing us to reconsider what words like origin or beginning even mean. And if the Big Bang was not the first, if the universe cycles through births and deaths, then what lies behind that rhythm? Is there a deeper order we have not glimpsed, a law that governs not just our universe but universes themselves? Then there is the riddle of dark matter and dark energy, the two great unknowns that dominate our cosmos yet remain invisible and unexplained. We know they shape everything. We know they determine the fate of the universe, but what are they? If dark matter is a particle, why can we not catch it? If dark energy is a property of space itself, why does it have the value it does? Even if we answer these questions, the triumph will not close the book. It will open a new one. Because to understand dark energy is to ask why space has energy at all, and to understand dark matter is to ask what other invisible worlds of physics are waiting hidden beyond our grasp. The universe has structured itself in layers, and peeling one back only reveals another. The question of life adds yet another dimension to the mystery. Are we alone in the cosmos, or are there others staring up at their skies, asking the same questions we ask? We search for exoplanets, we listen for signals, we analyze atmospheres for signs of biology, but so far the silence is deafening. If life is common, then where is everyone? If life is rare, then how improbable is our existence? Either answer is staggering. To live in a universe teeming with civilizations is to live in a cosmic community we cannot yet hear. To live in a universe where we are alone is to live with the weight of responsibility as the only known observers of all this immensity. Both outcomes change us. Both make us ask not just what the universe is, but what our place in it means. Even the end of the universe, which seems like a final answer, is nothing of the sort. Heat death, Big Rip, Big Crunch, vacuum decay. Each theory explains the future, but each raises its own impossible questions. If the universe fades into silence, what is left? If it collapses and rebirths, what drives the cycle? If it tunnels into another state, where does that state lead? The end is not an end, but another door, and behind that door lies another horizon. The universe does not give conclusions, it gives continuations. To ask where it all ends is to discover that endings are illusions. The cosmos does not close the book. It writes endlessly, forever adding chapters we will never read. Perhaps the deepest questions are not about matter, energy, or time, but about why there is anything at all. Why does existence exist? Why does the universe follow laws rather than chaos? Why do the numbers line up so perfectly to allow stars, galaxies, and life? Some argue that the multiverse solves this, that infinite variations mean one universe had to allow life, and we just happen to live in it. But even that explanation dodges the deeper question. Why does the multiverse exist? Why does anything exist, rather than nothing? That may be the one question science can never answer, because any answer requires a framework, and the question itself asks why the framework exists. It is a loop with no exit, a question that sustains itself by defying resolution. And maybe that is the point. The questions that will never end are not obstacles to be conquered, they are companions on the journey. They keep us reaching, keep us humble, keep us human. If we ever solved everything, if the universe handed us its final secrets, wonder would vanish, and with it, a part of what makes us alive. The endlessness of mystery is not a curse but a gift, ensuring that no matter how advanced we become, there will always be something larger than us, something waiting in the dark to be imagined. For ordinary people, this can feel frustrating. We want answers, certainty, closure. But perhaps the greatest lesson the universe teaches is that certainty is an illusion and closure is unnecessary. We are finite beings in an infinite mystery, and that is enough. The night sky does not need to be fully explained to be beautiful. A galaxy does not need to reveal all its secrets to inspire awe. Mystery itself is the meaning, the reminder that we are small but capable of wonder, fleeting but capable of asking questions that stretch across eternity. And so we go on, building telescopes, running simulations, writing equations on chalkboards, and staring into the dark. We know the questions will never end, and still we ask them. That is the miracle of humanity, not that we solve everything, but that we refuse to stop searching. The universe hides, and we chase. It retreats, and we follow. The questions multiply, and so does our hunger to answer them. It is a dance without resolution, a pursuit without capture, and it may be the most meaningful thing we will ever do. In the end, the questions that will never end are not a burden. They are our inheritance. The cosmos has given us stardust, light, and time, and in return, we have given it curiosity. That trade, that endless cycle of mystery and wonder, may be the closest thing to meaning the universe has to offer. We are here, asking questions in a universe that refuses to be answered, and that is enough. The pursuit itself is the purpose. The endlessness of questions is the endlessness of life. In the end, after tracing the history of human misunderstanding, the hidden forces of dark matter and dark energy, the impossible scale of cosmic structures, the dreamlike possibility of the multiverse, and the grim speculation about how everything might die, we arrive at the same realization that has haunted thinkers since the first stargazers. The universe is stranger, larger, and more mysterious than we will ever comprehend. Each discovery has been a revelation, but each revelation has opened doors to questions so vast they almost feel like new universes of their own. We began with the belief that the stars circled above us in a neat dome, and now we wrestle with the idea that there may be infinite realities beyond our own, each governed by laws alien to us. That leap is staggering, not just because of the science behind it, but because of what it does to our place in the story. The horizon we cannot cross is not just a physical boundary, it is a metaphor for knowledge itself. No matter how far we push, there will always be limits, edges, mysteries that escape us. Galaxies drift beyond reach. The truth of dark matter slips through detectors, and the question of why there is something rather than nothing remains unanswered. Yet instead of despairing at these limits, we find meaning in them. The act of searching, of daring to ask impossible questions, becomes its own purpose. Perhaps the universe was never meant to be solved like a puzzle with a neat ending. Perhaps it was meant to be explored endlessly, with wonder as the reward and humility as the lesson. What makes this even more extraordinary is that out of all the cold void, out of all the silent stars, life emerged here, on this small world orbiting an ordinary star in a forgotten arm of a galaxy. And not just life, but life capable of curiosity, life capable of looking up and asking what lies beyond. That fact alone reframes the story. We are not the centre of the universe, but we are the voice within it, the ones who name the stars, map the galaxies, and imagine the endings. In us the cosmos becomes aware of itself, however briefly, and that awareness may be the rarest phenomenon of all. So perhaps the conclusion is not really a conclusion, but an invitation. To keep asking, to keep searching, to keep wondering even when the answers slip further away. Because mystery is not a void to be feared. It is a horizon to be cherished. It means the universe still has something left to give us, that discovery will never run dry. Every unanswered question is a sign that there is more to see, more to dream of, more to explore, and that endlessness, that refusal of the cosmos to be small or simple, is its greatest gift. We live in a universe that humbles us, confuses us, even terrifies us, but it also inspires us. It reminds us that our lives, though brief, unfold on the grandest stage imaginable. Every glance at the stars is a reminder that we are both insignificant in size and infinite in imagination. And maybe that is the real point, not to solve the universe, but to let it astonish us. Because in the face of all its darkness and all its silence, the cosmos gave us wonder, and wonder is enough.